S. Chan presents educational video lectures as per the new UGC curriculum. Difficult concepts made easy. Study anywhere, anytime.
In this part of the video, we will be covering some aspects of matrices and we'll be solving those equations.
If you want to study this topic in detail, refer to these books from S. Chan Publishing and Vikas Publishing House. Link is provided in the description box.
Welcome to S. Chand Academy and I am Anmol Bhatia. We are doing the course Business Mathematics. So the topic is System of Linear Equations and it's a part of the topic which is matrices. So initially what happens, we have a case that why this matrices is linked to the linear equations. So first and foremost, you have to look at the definition of the linear equation. So let's say an equation which is of the type x plus 3y equals to 9. This particular equation is called as a linear equation. And that linear equation can be in terms of two variables or it can be in terms of three variables. They are also known as unknowns. And the graph of this equation is a straight line and that straight line graph would be there in the xy plane. And the pair of values which are the x values and y values that satisfies this particular equation is known as the solution of that particular linear equation. So here we have this system of linear equations and we want to link matrices into these system of linear equations so as to find out a solution to that particular problem. So the definition is a linear equation which is there in n variables, let's say x1, x2 till xn, has this form a1x1 plus a2x2 plus a3x3 so on up till an xn, that is equal to b, where the coefficients of this a1, a2 and a3 up till an are there and b are the real numbers. B indicate that real number which is connected to that set of equation. So this is a particular definition which is related to the linear equation. Now we have to look for certain solutions of the linear equations. Let's say we have these two equations, x plus 3y equals to 9 and minus 2x plus y equals to minus 4. So we have these two equations and after making the graph we can see that these two lines intersect at this particular point which is 3, 2. That means it has a unique solution. So in case of the equations which are of this type, which has only one solution, that is called as a unique solution. Another equation, let's say of this type, maybe these equations which are having two parallel lines and the lines are majorly parallel and they are not intersecting at one particular point, that is called as no solution. And you have another equation which is 4x minus 2y equal to 6 and 6x minus 3y equals to 9. And when you look at this equation specifically, both the two equations end up with the same set of equation. So that means both the equation will have the same graph and it is called as a many solution type case. And this is specifically for the case when you have two variables. Now what happens when you have three variables associated? So when you have three variables associated with the system of linear equations, it can have a graphical presentation which is of 3D and in that you have one common point which is this point that may have a particular solution that would be a unique solution, or this might be a case of A, B and C. In case of no solution, these three different planes would not overlap or intersect with each other. That means there is no intersection of all these points. That means it has no solution. And for the next set, it has many solutions. That means the line would be, the two planes would be intersecting at many locations. That means let's say P and Q are the two different locations on which they are intersecting. That means we have many solutions that can be derived or that can be achieved from this particular set. So what happens, we are particularly interested in finding out a solution of the three linear equations, and the points lies on the three different planes. Let's say for an example, we have this equation, these three different equations, in which x1 plus x2 plus x3 is equal to 2 mentioned, 2x1 plus 3x2 plus x3 mentioned as 3, and x1 minus x2 minus 2x3 equals to minus 6. And we have the system of linear equations, and we want to solve it with the help of this Gauss-Jordan elimination. And I'll be correlating with an algebraic formulation and with a matrix method in which you would be able to solve these two equations simultaneously. So we'll be learning about the method, and you will be looking at the aspect in which both the methods are similar or not. So here you have certain definitions before coming into that matrix incorporation. The first thing is, what is a matrix? So matrix is a rectangular array of numbers, and the number of arrays are called as elements, and these are specifically called as elements of the matrix. Let's say I have these examples like 2, 3, minus 4, 7, 5, 1. Here 2 is an element, 3 is an element, minus 4 is an element, and all these combinations is connected to a matrix, and that is called as an A matrix. This is called as a B matrix. This is called as a C matrix. It has a particular order, and internally it has a particular elements. Now the matrix may have rows and it may have columns. Like if it is A matrix, it has 2, 3, minus 4, 7, 5, 1 written. That means this would be your first row, this is your second row, and this particularly is your column, this is your another column, this is a third column. Then you have a submatrix. A submatrix is a matrix which can be obtained from the internal aspect of any matrix. Let's say you have a matrix A, and from that matrix A you have this 1, 7 and 2, 3 and 5, 1. You have found out this one submatrix. So that submatrix is the matrix which is from the major matrix. So 7, 3, 1 is also a submatrix of a matrix, and when you have 1, 5, 4 and minus 2, and 1, 5, 4 and minus 2, this is also a submatrix of A. Then you have a size and the type of matrix to be defined. Size indicates the order of the matrix. Order indicates the particular format, which is m cross n, that means row into the column. So if you have this matrix, so you have number of rows 2 and you have the number of columns as 3. So 2 cross 3 would be the size or the order of this matrix. Another matrix is, let's say, of 3 by 3 order, and this is called as square matrix because you have 3 rows and 3 columns predefined. Another, here you have only one row and you have 4 different columns associated. That means you are having this matrix in a row manner. So we name it as a row matrix, and if you have the matrix in a column fashion, you name it as a column matrix. Now, as far as these locations are concerned, and if A is given to you, and you need to check whether this location is called what. So this location is particularly called as A11 because this is first row and first column. If this location is required, so this location is called as A12 and then A13 and so on. So if you want A13 value, so A13 would be this location. And A21 is the second row first column, so this is the second row first column. Apart from that, you have the diagonal matrix in which specifically these identity matrices are there, in which you have the two numbers which are 1 to be placed here and rest of the numbers identities are 0. And here also you have the diagonal placement of the numbers and others are placed as 0. Then there is a particular relationship that I was talking about, that there is a relationship between the systems of linear equations of the matrices, and you have a matrix coefficient and the augmented matrix you have. Let's say you have this equation, and in that equation, if you want to convert this particular equation in terms of a matrix, so for that you have the coefficient which is 1, you have this coefficient 1, you have this coefficient 1. This can be written as 1, 1, 1, then 2, 3, 1. This is 2, 3, 1, then 1 minus 1 minus 2. So 1 minus 1 minus 2. This would be the matrix of the coefficient. And if I want to club that coefficient matrix with the solution matrix, so I need to augment it with the solution matrix like 1, 1, 1, 2, 3, 1, 1, minus 1, 2, and I need to write it with a specific line, and I need to write the values 2, 3, minus 6, and that is particularly called as an augmented matrix. Now, what I want to link the normal set of equations, which is, let's say, the normal method of eliminations or substitution. I want to link that particular stuff with the matrices. So for that, I'll be requiring certain transformations, and those transformations are basically called as elementary transformations or elementary row transformations. So elementary transformations are interchanging or interchange the two equations. Here we interchange two rows of a matrix. So let's say if we have a matrix and we want to interchange row 1 with the row 2, we can do that by applying that row transformations. Here also we can do that with the help of elementary transformation. Now let's say if we want to multiply both the sides of an equation by a non-zero constant. Let's say you have an equation which is x plus y plus z equals to 4, and I have something in my mind to multiply the equations with 2, and I need to subtract another set of equation, and after subtraction I'll get an elimination of any variable, let's say x or y. So for that I can do that. Here also I can multiply the terms with any row with a non-zero constant. Then the next part is you need to add a multiple of one equation into another equation. Let's say you have this equation 2x plus 3y plus 4z equals to 6, and you have another which is minus 2x plus 3y plus 8z equals to 2, and you need to add both the terms so that one set of variable is eliminated. So for that particular equation you can add them. This would become 6y plus 12z equals to 8. In terms of matrices also you can perform the row operation. Let's say you have the first row, you have the second row. So what is required, you can do this row operation by using this R1 plus R2 term. So you can also apply this row operation by multiplying the elements with one row and adding it to the corresponding elements of another row. So the process is similar of the row transformation and the general elementary transformation. Let's have a look at this general elementary transformation and the row transformation together. So you have this equation which is the same equation. So you have x1 plus x2 plus x3 equals to 2, 2x1 plus 3x2 plus x3 equals to 3, x1 minus x2 minus 2x3 equals to minus 6. So you have written the same set of equations here. So what I have done, I need to add the two equations together and I need to eliminate the first element. So what I have done, I have multiplied this first equation by a minus 2 and added it into the second equation so that my first part is eliminated. Similarly, for the next set, I have this x1 plus x2 plus x3 and x1 minus x2 plus 2 minus 2x3. I can easily subtract both the terms and I may get these two cancelled out. So what do I get? I will get this set of equations which are left out, and in the similar manner, if I want to convert it into a matrix term, what I can do, I can use this augmented matrix. So augmented matrix is the coefficient matrix which is 1, 1 and 1. This is 1, 1, 1, 2, 3, 1, 1 minus 1 and minus 2, and it is augmented with the solution which is 2, 3 and minus 6. So it is augmented with the solution. Now what is my requirement? I need to make this matrix as 0. I need to get majority of the numbers to be 0 so that these terms are eliminated. So what am I doing here? I need to make this 2 as 0. So what I'll do, I'll use this operation R2 changes to R2 minus 2R minus 2R1. So I'll multiply this first row by 2 and subtract it from the second. So 2 minus 2 into 1, 3 minus 2 into 1, 1 minus 2 into 1, get these elements. And similarly for the next, R3 changes to R3 minus R1 minus 1, R3 changes to R3 minus R1, so I need to subtract it from here also, and here I'll get the elements. So I'll be getting that same elements when these two operations are performed. So you can check that the first equation remains the same because I have not done any operation on it. And then in the second equation, I have subtracted it so that this first term gets cancelled and I am only left with the second and third coefficient and a -1 because I have subtracted them. Then the third equation is also changed, like I have subtracted both the terms and I'll get this final equation. So far we have got the similar results in terms of this elementary transformations and in terms of this elementary row transformation. Then what do? We can keep this equations as similar, and now I want to eliminate these x2 terms. So for that, what I can do, I can keep the second equation as same, and from that second equation I can subtract the first equation because I need to cancel them too. So I have used this equation 1 minus equation 2. So I can use this term so that I have subtracted these two. Then equation 3 plus 2 times equation number 2. So equation 3 is this, and 2 times equation 2 would give me 2 into x2. So 2 into x2 positive side minus 2 into x2 is negative. When I add them, I'll get a 0 there. That means these two terms would be cancelled out. So what do I get? I'll get these equations so that when I do the cancellation, I'll end up or I'll land into these results. That is my final solution. And if I talk about that augmented matrix, which is this matrix, in the same fashion, I need to move ahead. Like if I need to make this element as 0, because diagonally I can keep this as 1. And I need to remove those elements from 0. So I need to use this operation, which is R1 changes to R1 minus R2. So first row's element and the second row elements needs to be subtracted. So I have subtracted these two elements. And similarly for the third row also, these elements are to be subtracted from the second. So I'll get this. After applying those row operations simultaneously, like 5 is an additional part, so I have divided this row by 5. So I'll get these elements, and ultimately after applying those row operations, I'll get these results. That means when I get the final result, so my final result would be x1, which is 1. The coefficient of x1 would be x1. x1 is equal to -1, x2 equals to 1, and x3 equals to 2. So I'll get these elements as a set of my final equation. So when I use the elementary transformation, I'll get these results, and when I use this elementary row transformation, I'll get these results. So that means these two are somewhat interconnected. That means when I am performing these kind of operations, I need to write majority of the equations many a times. But whenever I use a matrix, it would give me a cleaner picture, and that would be easy to solve as compared to the general method. That's why we have used this elimination method, which is a Gauss elimination method, to find a particular set of solutions. So this is the case related to finding out the solution for that particular problem. We stop here for a short break. After coming back from the break, we will learn this concept of equation solving through matrices in a more simplified manner.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on UGC curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting within the comfort of your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back to S. Chand Academy after the break. Before going to the break, we have learned the concept of Gauss elimination method, which is used to solve a particular set of equations with the help of row transformations. And we have seen particularly in the case of one solution, which is the unique solution. Now in this part of the video, we'll be learning the case of many solutions and also other methods associated with the same concept. So let us have a look at the example, which is related to many solutions, in which you can see that you have to solve the system of linear equations, and this system has this particular set of equations aligned. That means you have x1 minus x2 plus x3 equals to b1, here b2, here b3, and b1, b2, b3 are connected to these three solutions. That means there are many solutions associated with the with one set of equation. So what to do with many sets? I have told you that we have to augment the matrix together with the particular coefficient matrix. So the coefficient matrix that is to be formed from this particular set is 1, minus 1 and 3. I have written 1, minus 1 and 3. Then 2, minus 1 and 4. So 2, minus 1 and 4. Then minus 1, 2 and minus 4. So minus 1, 2 and minus 4. And then a line, that means a matrix would be augmented with the solution matrix. So the solution matrix are 8, 11 and minus 11. That may be 0, 1, 2 and 3, 3 and minus 4. Now what is to be done? Our aim is to convert this initial set of matrix into an identity matrix. So we'll be doing that by a set of row operations. So we have 2 here and we have minus 1 here. So what row operation will apply? We use this second row and we use this operation R2 changes to R2 minus R1, R2 minus twice of R1, which is this first operation. And the second operation is minus 1 added to 1 would give you 0. So R3 changes to R3 plus R1, which is this set. So I need to use this particular set in order to solve that equation. So what happens after applying that row operation, we will end up with these two zeros. Now what I want, I have applied the entire row operation throughout this equation. Now what I'll do, I'll use this first row to make it 0. So minus 1 is there. So I can use this minus 1 and use the row operation to be added to the next set of row operation, so that the first part, which is the second element of the first row, becomes 0. So R1 changes to R2 is my row operation that I'll be applying. And the next row operation is R3 changes to R3 minus R2. So R3 is this row operation. R3 changes to R3 minus R2. That means 1. When I add this into the second row, which is this row, so I'll get a 0. So R3 changes to R3 minus R1. I'll get a 0 there again in the third row. And consecutively, all the other elements will be changed. So I'll get these updated elements as my matrix. And again, I want to have 0 in this part because diagonally I got 0. But for these, I need to make them 0. So for that, I may apply the row operation 1 and the row operation 2 for the first row and for the second row. So after applying these row operation, I got a term which is a reduced matrix term. And from here, I'll have the 3 different solutions, which are many solution cases. So the first solution is this solution, which indicates that x1 is 1 and x2 is minus 1 and x3 is 2. This is my first solution. The second solution indicates that x1 is 0, x2 is 3 and x3 is 1. And the next set of equation is x1 as minus 2, x2 as 1 and x3 as 2. So this is the next set of equation. So that means for many solution equations also, this method is applicable, and the method is apply the row operations in order to get those elements as 0 and finding out the final answer as the solution. Now the method that we have understood so far is the Gauss-Jordan elimination method. And what is the definition of this method is a matrix is in the reduced echelon form. Reduced echelon form means what? That any row consisting entirely of zeros are grouped at the bottom of the matrix. That means we need to group all the rows which are connected to the bottom of the matrix. The first non-zero element of each other row is 1 and the element is called as a leading one. This leading one of each row after the first is positioned to the right of the leading one of the previous row. And the next set of elements which are connected to this leading one should be 0. That means we show you certain examples which is called as a reduced echelon form. So this is a case of a reduced echelon form in which you got a diagonal matrix and remaining elements, these elements can be 0. But this is not an example of a reduced echelon form, because this is not becoming an identity matrix. Rather, this may be an example of a reduced echelon form and all the other elements can be 0. But here also you get 1 and you get all the elements as 0. This is also not an example of a reduced echelon form. So by looking at this matrix, you can easily judge that which one is a reduced echelon form and which is not. So I have told you that in the Gauss-Jordan elimination, you have to augment the two matrices together, like A is to be augmented with B, and we need to get a reduced echelon form. That means we try to make it as an identity matrix, and here we will get the solution. So from this step, we will find the solution to the particular problem. Let's have an example of this Gauss-Jordan elimination, and after that we have a solution. So the method says that you need to convert it into a reduced echelon form and find out a particular solution. So here I have augmented the matrix together. So I have this matrix which is augmented together, and what I need to do, I need to convert it into a reduced echelon form. So for that particular situation, I need to have 1 here on the topmost corner of this row. So what I will do, I will be converting the two rows together. So R1 is converted to R2, or R1 interchanges to R2. That means you will get 3, 3, minus 3, 9 and 12, and rest of the rows are remaining the same. And here if I want 1, so I need to divide the entire row by 1. So this is the row operation. After dividing it, I will get this elimination procedure done. And then what I do, I'll have to use, or I have to make this 4 as 0. So how can I do that? I need to get this 4, and this would be the row number 3. So row 3 minus 4 times row 1. So row 3 minus 4 times row 1 would be the case. And then depending upon the reduced echelon form, I need to make this 2, because I got 2 here from this row operation. So I got 2 here. So dividing the entire row by 2 will hardly make any difference. Rather, I will get 1 more. So I will be dividing this entire row by 2. So after doing it, I will get this 1 minus 1 and 1 done. And additionally, I have these elements clubbed. So what is the case? I need to have this element as 0. So in order to make this element as 0, I need to apply this row operation together. So after applying those set of row operations, I will get this reduced element, which is in terms of a reduced echelon form. So you can see that it is a case of reduced echelon form, and you will get this final matrix as a part of your solution. So this was your first example, which is related to the solution of the general system of equations. Another set of example is you need to solve if possible, it is written. If possible means if the solution exists, you need to solve this particular equations. So you have 3 different equations as the question says, and in that you have 3 minus 3, 3, 2 minus 1, 4 and 3 minus 5 minus 1, which is augmented with 9, 7, 7. So we need to look for a solution, and in that I have told you that you need to reduce it into a reduced echelon form. So you have 3 here. So you need to divide the entire row by 3 so that it becomes 1. So it becomes 1 minus 1, 1 and 3, and the next rows remain same. Now our next target is to make these two elements as 0. So how can I do that? I need to apply that row operation, which is R2 changes to R2 minus 2R1, R3 changes to R3 minus 3R1. So I have applied this same step in order to get my values. So then you have reduced it into this term, and finally you have this pivot element, and you need to use this pivot element to make this element as 0. So what you have done to make this element or the next set of elements as 0. So what you have applied the first row, which is the row 1 changes to row 1 plus row 2. So this is your row operation, and the next operation is row 3 changes to row 3 plus 2 times row 2. After applying that row operation, you have reduced it into a set of equation which can be written as a reduced echelon form. Now after getting this final matrix, now it cannot be reduced any further now, because if I apply any row operation, this sequence may change. So I don't want to lose my echelon form here. So what I can do, I can generally use the equations to solve. Like we have x1 associated with this 1 and x3 associated with this 3. So I have this x1 plus 3x3 which is equal to 4. Then I have x2 plus 2x3, that would be equal to 1. So I have these two equations connected. So from these two equations, what I can do, I can easily find out x1's value and x2 value. So I can find out x1 and x2 values. So what I have got these two variables x1 and x3 in terms of x2. So the question was saying that if possible, you can solve it. So I can easily see that this is dependent on this x3 value. So what I can do, I can have a general solution like x3 can have any value which can be r. So I can substitute r here. So x1 would be minus 3r plus 4 and x2 is minus 2r plus 1 and x3 value can be assumed like r can be any real number for that particular parameter. This is the case of that particular equation. And lastly, you have the case of the equation which is a multi-system equation. That means it may have a many solution case. So you have 2, minus 4, 12, minus 10 and all these numbers. So you have taken or you have written these elements and augmented it together. So what you have done, you have used this 2 to make it 1. So I have divided the entire row by 2 so that it became 1, and this matrix element is transformed easily. Now what is required, I need to make this element as 0 and make this element as again 0. So what I can do, I need to subtract R2 from R2 and R1 needs to be added up. So R2 and R1 needs to be added up, and similarly R3 changes to R3 minus 2R1. That would be the case. So I have used these two zeros together, and similarly for other aspects these remain same. Here you got a pivot element again. That means I need to divide the entire row by 3. So if it is done, or if it is divided entirely by 3, so what it does, it will lead to 1, and then apply the same usual operations to make it reduced into the echelon form. So you got a reduced echelon form here. Now you can see that you have x1 variable here, you have minus 2x2 and 0, 0 there. So you can get an equation which is this equation, and the next equation is this x3 equals to 6 and x4 equals to 1. So you got these results, and this x1 can be treated in terms of x2, so which would be minus 2 plus 2x2. So you can put that x2 as r. So in terms of these r values, you can find the answer. Now, as far as we have seen the cases of these elimination method, which is a Gauss elimination method, but herein we have a particular case in which the equation can be a homogeneous system of equation. It can have a homogeneous system of equations. Now, what is this homogeneous system of equations? A system of linear equation is said to be homogeneous if the constant terms are 0. That means you have this type of equation in which the right hand side coefficients are 0. That means you may observe that x1 equals to 0 and x2 may be equals to 0 and x3 equals to 0 may be the solution. If I substitute x1 as 0, x2 as 0 and x3 as 0, that might be a solution. And that particular solution is known as a trivial solution, right? But we would be particularly interested in finding out the answer associated to that non-trivial solution. So for that, the method remains the same. That means we have to augment that coefficient matrix, which is 1, 2 and minus 5, minus 2, minus 3 and 6 with zeros. So I have augmented this matrix with zeros and applied the row operations, which is the row operation is R2 changes to R2 plus 2R1, that becomes 0. This would automatically be changed by applying that row operation. So finally you will get this augmented matrix, or finally you will get the reduced matrix. Now what is to be done? I may assume this as an equation like x1 plus 3x2, that would be equal to 0, and another equation is x2 minus 4x3, that would be equal to 0. That means I can find out x1 in terms of x2 and x3 also in terms of x2. So here x3 can be assumed as one set of variable as r, and in terms of r I can find out the other variables. Also it can be the other way around, which may be x1 and x2, x1 and x3 to be calculated in terms of x2 values. Now that is the theorem 2, in which it says that the system of linear homogeneous equation has more variables than the equation, and that may have many solutions, or those many solutions are termed or can be represented in terms of r only. So this is the case of homogeneous system of equations. So with this we come to the end of the video, in which we learned about certain basic concepts related to matrices. We have learned about a solution which is related to the solution of the particular equations, and ultimately we have seen those Gauss elimination methods for a general case and for the case of homogeneous representation. Thank you.
If you want to study this topic in detail, refer to these books from S. Chand Publishing and Vikas Publishing House. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.